Hi guys, welcome to another episode of Learn with Sir Glenn, and for this lesson, we're going to discuss fundamental counting principles. So, let's go! So before we proceed with our topic, let's have some terms to remember when we discuss about the fundamental counting principle. So the first one is experiment. In the fundamental counting principles, when you say experiment, it is any activity with an observable result such as tossing a coin, rolling a die, choosing a card, and etc. Next is the outcome. The outcome is the result of an experiment. For example, if you toss a coin and you get a head, head is your outcome. Or if you're going to roll a die and you get 1, then that will be your outcome. Next, the sample space is the set of all possible outcomes. So when you toss a coin, the possible outcomes are head or tail. When you roll a die, the possible outcomes are 1, 2, 3, 4, 5, and 6. So the set of possible outcomes will give you the sample space. Then we have the event, which is a subset of a sample space. So for example, when you're tossing a coin, you can have the event of getting head. When rolling a die, you can have the event of getting 3. Okay, so when you say fundamental counting principle, we're actually counting the number of ways, or the number of sample space, or the number of outcomes. So for example, let's have this problem. I want you to meet Pedro. Pedro wants to do an OOTD for his Instagram post. And unfortunately, these are the only remaining clothes on his cabinet. So we have the long sleeves, polo shirt and t-shirt, the shorts and the pants, and 3 pairs of shoes, the black shoes, brown shoes, and white shoes. So how many OOTD can Pedro have using these clothes? So on this problem, making an OOTD is our experiment. And since we want to find the number of OOTD, then we are actually getting the sample space. So since we are counting the sample space, we can make use of the fundamental counting principle. So when counting your outcomes, or when you're trying to get your sample space or the number of your sample space, you can actually use two methods. So the first one is using tree diagram, and the second one is using the fundamental counting principle, which is our topic for this video. So first, let's try the tree diagram. So from the word itself, the tree diagram is making use of a diagram which is similar to a tree with a trunk and branches. So now let's try the tree diagram. So tree diagram. So first, Pedro can choose between long sleeve, polo shirt, or t-shirts. Then if Pedro chooses the long sleeves, we can have shorts or pants. Then the same thing with the polo shirt, we can have short and pants. And so with the t-shirt, short and pants. Then if Pedro chooses the shorts, you can pair it with white shoes, black shoes, and brown shoes. Then you will have the first set of OOTDs. So we have here long sleeve, shorts, white shoes, long sleeves, shorts, black shoes, long sleeve, short, and brown shoes. And this will happen to the rest of our set. So therefore, counting the OOTDs that we can have on this tree diagram, we have 18 OOTD. So let's have another example of tree diagram. A new polo shirt is released in 4 different colors and 3 different sizes. So how many different colors and size combinations are available to the public? So solving for this using the tree diagram, so let's assign the colors as red, blue, green, and yellow, and the sizes, which are small, medium, large, which are the common sizes that we have for the t-shirts. Making a tree diagram, let's have the red polo shirt first. So this can have small, medium, large. So therefore, the first set of choices or combination of polo shirts that we were going to have will be small red, medium red, large red. Then let's have the blue. So small, medium, large. Then green, small, medium, large. Then yellow, small, medium, large. So therefore, using 4 colors and 3 sizes, we can have 12 different choices for the polo shirt, or 12 different combinations. And obviously, using a tree diagram is time consuming, especially if you have many selections or many options. So for this one, you only have 4, but what if you have 26, or what if you have 15 colors and 7 sizes. Using a tree diagram to find the number of outcomes will take time. So what we're going to do is to make use of the counting principle. So the counting principle, you may have the addition principle of counting, and according to this one, if you have two events which are mutually exclusive events, meaning there are no common outcomes, so let's say those are the event A, which can occur in M ways, and event B can occur in N ways, then event A or B can happen in M plus N ways. So what do you mean by this addition principle of counting? So to make it easier to explain, let's have an example. So let's say Jose wants to go to Pasay. So he can choose from 3 bus services or 4 jeep services to head from home to Pasay. So how many choices does Jose have for his service to Pasay? So since we have here event for buses and event for the jeeps, and these events are mutually exclusive, then if you want to find the number of choices for Jose for his service from home to Pasay, you're just going to add the choices per event. So therefore we have 3 plus 4, which is 7. So 3 from the bus services and 4 from the jeep services. So this is addition principle of count. Let's proceed to the next one, which is the fundamental counting principle. Which is for this one, we have the multiplication principle of counting. So this applies when we are making more than one selection. So let's say you have two events. Event A can occur in M ways and event B can occur in N ways. Then the number of ways that both can occur is M times N. This one is applicable with our previous problems. So just like the problem of Pedro and the problem of polo shirts combination. How to use the multiplication principle of counting in finding the possible outcomes. So let's say we have the problem opener about Pedro. So according to the multiplication principle of counting, we can use this one if we have more than one selection. And Pedro will have 3 selections here. Pedro will select what to wear on the top, what to wear on the bottom, and what pair of shoes to wear. So therefore, there will be 3 selections. So if you want to solve for this one, according to the multiplication principle of counting, first, you have to identify your selections. So we have here the tops, the bottoms, and the pair of shoes. So according to the multiplication principle of counting, you're just going to multiply the choices for your events. So we have the event for the tops, event for the bottoms, event for the pair of shoes. So therefore, we will have 3 times 2 times 3, which will give you 18 OOTD. Which is the same as what we have using the tree diagram. Okay, so let's have another example. This time, let's use it on a new polo shirt problem. So a new polo shirt is released in 4 different colors and 3 different sizes. So how many different color and size combination are available to the public? Tree diagram, we're able to get 12 different choices. So now let's try to solve it using the fundamental counting principle. So since we have here 2 selections, a selection of colors and selection of size, so we will have number of possible colors, which is 4, and numbers of possible sizes, which is 3. So the selection per color and the selection per size, then we multiply the number of choices per selection, so that will give us 4 times 3, which is equal to 12. So we will have the same answer with our tree diagram. So in solving for the possible outcomes using the fundamental counting principles, there are 2 things that you have to remember. So first, you get the number of selections, or these will be also your events. Then after that, find the number of ways or the choices for your selections. So for example, we have this problem. So at a restaurant, you have the choice of 4 different main courses, 5 different drinks, and 6 different desserts. So how many different meals, 1 choice of each, can you choose? So since you're going to make a meal composed of main course, dessert, and drinks, there will be 3 selections. So the first one, you're going to choose from the main course. Then you're going to choose for your drink. You're going to choose your dessert. So therefore, there will be 3 events or 3 selections. So for the main course, there will be 4 choices. For the drinks, there will be 5 choices. And for the desserts, there will be 6 choices. So according to the multiplication principle of counting, to get the possible number of outcomes or the sample space, we multiply the choices per events. So therefore, we will have 4 times 5 times 6, which will give you 120. Okay, so let's have another example. So 3 small towns designated by A, B, and C are interconnected such that there are 3 different roads from A to B and 5 different roads from B to C. How many ways can you travel from town A to town C via town B? So for this one, we will going to have 2 selections. So the first one is if you travel from A to B, we're going to choose from 3 different roads. Then next one is when you travel from B to C, you're going to choose from 5 different roads. So A to B will have 3 choices, B to C will have 5 choices. So multiplying this will give you 15. So therefore, you have 15 different ways when you want to travel from A to C via town B. Okay, so let's have another example. So how many ways can you answer a 5 true or false question? So again, first what you're going to do is to find the number of your selections or how many times you have to select something. So for this one, we're going to have 5 selections because you're going to choose answer from 5 item true or false questions. So we have the item number 1, item number 2, item number 3, item number 4, and item number 5. So since this is true or false, for the item number 1, you're going to choose between 2 choices, which is true or false. Then same thing with the item number 2, item number 3, item number 4, and item number 5. So all we have to do now is to multiply the set of numbers, which will give us 2 times 2 times 2 times 2 times 2, which is 32. So there are 32 ways to answer a 5 true or false question. Okay, so let's have another one. A plate number system consists of 2 numbers and 2 letters. So how many plate numbers are there in the system? So if you're going to have this kind of system for your plate numbers, then you will have 4 selections. So those are the 2 numbers and the 2 letters. So the first selection will be a number, second selection is another number, then we have the letter and another letter. So if you're going to choose a number, there will be 10 choices. So that will be from 0 to 9. So therefore we have here 10. Then you're going to choose another number. So there will be another 10 choices. Then if you're going to choose a letter, there will be 26 letters. So from A to Z, then we will have another 26. So all you have to do is to multiply the set of numbers to get the number of plate numbers that we can have using this kind of system. So therefore we will have 10 times 10 times 26 times 26 will give you 67,600. So there will be 67,600 plate numbers using this system. Okay, so let's have another example. So how many 4-digit number can be formed using 1, 2, 3, 4, 5, 6 if repetition is allowed? Since we have here a condition that we can repeat the numbers and we are going to make a 4-digit number, we will have a number up to 1,000. So therefore, we're going to have 4 selections. So the first selection is for the thousands place, for the hundreds place, tens place, then ones place. So all you have to do now is to get the number of choices or the number of ways for every selection. So for the thousands place, we can choose from the numbers 1 to 6 since we're going to use this set of numbers. Then since repetition is allowed on the hundreds place, we can still use those numbers which are 1, 2, 3, 4, 5, 6. So therefore, we will have 6 choices. Then same thing that will happen to your tens. We can have 6 choices, still 1, 2, 3, 4, 5, 6. Then for the ones, we can still use those 1, 2, 3, 4, 5, 6. So therefore, we will have 6 times 6 times 6 times 6, which is 1,296. So let's have another example. So it is almost the same with the previous one, but this time we have here a condition, which is repetition is not allowed. So how many 4-digit number can be formed using 1, 2, 3, 4, 5, 6 if repetition is not allowed? So meaning, we cannot use the number once we already use it on our selection. So for example, we have here the thousands, hundreds, tens, and ones. If you're going to choose a number for your thousands place, you can actually choose from 1 to 6. So therefore, there will be 6 choices. Since you already have a number on your thousands place, you cannot choose that number on your hundreds place because repetition is not allowed. From 6 choices, we're going to remove one number from our choices because we already put it on our thousands place. So therefore, on the hundreds place, we're going to have only 5 choices. For the tens place, we're going to have 4 choices because we have to remove another one number from our choices because we already put it on the hundreds place. Then for the ones place, we're going to have only 3 choices because we have to remove again another one for our tens place. So therefore, we will have 6 times 5 times 4 times 3, which will give us 360 4-digit numbers. So therefore, we can form 360 4-digit numbers using 1, 2, 3, 4, 5, 6 if the repetition is not allowed. Okay, so let's have another one. So how many 4-digit number can be formed using 1, 2, 3, 4, 5, 6 if the number must be an even number? So same problem but different conditions. So thousands place, hundreds place, tens place, and ones place. So since we're given the condition that the number must be even number, for us to have an even number, the last digit of your number should be an even number. So meaning your last digit is either 0, 2, 4, 6, 8. So on our choices, we only have 3 even numbers, which are 2, 4, and 6. So therefore, on our last digit, which is the ones digit, we only have 3 choices. So therefore, we're going to put 3 on ones digit. So these 3 are the 2, 4, 6 on the numbers that we can use. So on the thousands place, since there are no conditions, so we can have any of those 6 numbers. So therefore, we will have 6 choices. And for the hundreds place, we can have any of those numbers again. So therefore, we will have 6 choices. And so with the tens place, 6 choices. So multiplying 6 times 6 times 6 times 3 will give you 648. You can make 648 4-digit even numbers using 1, 2, 3, 4, 5, and 6. Okay, so let's have another one. So in a class of 6 boys and 4 girls, how many ways can a teacher choose his president, vice president, and secretary if anyone can be placed on any position? So again, we have to identify first our selections. So we are going to have a selection for president, a selection for vice president, and a selection for secretary. An event for president, an event for vice president, and an event for secretary. If a teacher will choose his president, so anyone can be placed on any position. So therefore, we can have the 6 boys and the 4 girls on the president's position. So therefore, we will have 10 choices. Then for the vice president, we're going to only have 9 choices because we already have the 1 student on our president position. So from 10 choices, we remove 1 student because that student's already the president. There will be only 9 choices for your vice president. Then for the secretary, we will only have 8 choices because we have to remove another one from the choices for our vice president. So multiplying this number will give you 720. 10 horses are in a race. So how many ways can a first place, second place, and third place be chosen? So again, you have to identify your selections or your events. So first selection will be the selection for the first place, selection for the second place, and selection for the third place. After this, you have to identify your choices per selection. So for the first place, you can choose among the 10 horses. So you will have 10. For the second place, we can only choose out of 9 remaining horses because one of the horses already in the first place. Then on the third place, we can only choose from the remaining 8 horses. So multiplying these numbers will give you 720. So there are 720 ways of choosing first, second, and third place for 10 horses in a race. Let's have another one. So in how many ways can Sheila, Anna, Joy, Julius, and Donna be arranged in a row? So since you're going to arrange 5 persons in a row, there will be 5 selections. So selection for the first person, selection for the second person, third person, fourth person, fifth person on a row. So for the first person, we can choose among the 5. So therefore, we will have 5 choices. Then for the second person, we can only choose from the remaining 4 persons because one of the persons already on the first person position. Then on the third person, we can only choose from the remaining 3 persons. On the fourth position, we can only choose from 2 remaining persons. Then we only have 1 remaining person. So after this, we multiply the set of numbers and we will have 120. We can have 120 arrangement of 5 persons in a row. Okay, so let's have another one, but this is almost the same problem with a given condition. So how many ways can Sheila, Anna, Joy, Julius, and Donna be arranged in a row if Julius and Donna should be together? So this is almost the same with the previous one, except that this time there's a condition that Julius and Donna should be together. So let's say you have here Sheila, Anna, Joy, Julius, and Donna. So since in the condition that Donna and Julius should be together, what we're going to do is to bind them. So whenever you have to arrange objects and there's a condition that some of the objects should be together, what we're going to do is to bind those objects. So for this one, since Julius and Donna should be together, we're going to bind Julius and Donna, and when we do that, Julius and Donna will become one object. So therefore, instead of arranging 5 objects, we're going to arrange 4 objects, including the binded Julius and Donna. So we will only have 4 places to arrange, or 4 persons or 4 objects to arrange. So there will be 4 places. So for the place number 1, we can choose among the 4. For the place number 2, we can choose among the 3. For the place number 3, we will have 2. For the place number 4, we will have 1. Okay, so but again, you have to remember that Julius and Donna can switch position. So for this one, we have here Donna and Julius position, but when you switch the position or when you rearrange the position of Julius and Donna, you can also have Julius Donna. So that will give you another set of arrangement, which is different from the previous arrangements that we have. So therefore, there will be 2 sets of 4, 3, 2, 1, and we're just going to have multiply this by 2. So the first arrangement will be Donna Julius. So that will give us 4 times 3 times 2 times 1. Then the another arrangement is Julius Donna, interchanging the position of Donna and Julius. So that will give us another 4 times 3 times 2 times 1. So instead of solving for 2 different set of arrangements, we're just going to multiply this by 2, which is the number of arrangement that we can have with Julius and Donna. So therefore, we will have 4 times 3 times 2 times 1, which is the arrangement that we can have. Then we multiply it by 2 for the arrangement of Julius and Donna. So there will be 48 arrangements that we can have where Julius and Donna are together. Okay, so let's have another one. So this is almost the same with the previous one with a different condition. So in how many ways can Sheila, Anna, Joy, Julius, and Donna be arranged in a row if Julius and Donna should not be together? So in our previous examples, we already solved for the total number of arrangements and for the arrangement of Julius and Donna together. Then for this one, we're going to look for the arrangement where Julius and Donna are not together. So for all possible arrangements, this is the first one, which is 120. Then for the arrangement where Julius and Donna are together, we're able to get 48. Then all we have to do now is to look for the arrangement where Donna and Julius are not together. So if you notice, all possible arrangements will include the arrangement where Julius and Donna are together and Julius and Donna are not together. So meaning, if we remove the arrangement where Julius and Donna are together out of all possible arrangement, what will left will be the arrangement where Julius and Donna are not together. So all we have to do is to subtract the all possible arrangements minus the arrangement where Julius and Donna are together to get the arrangement where Julius and Donna are not together. So therefore, we will have 120 minus 48, which will give us 72. So among the 120 arrangements that we can have with these 5 persons, 72 of those arrangements or arrangements where Donna and Julius are not together. 48 of those arrangements are arrangement where Donna and Julius are together. So okay, that's it. Thank you for watching and hope you have learned something from this video.